What's up everyone, this is Andy, and as you heavily requested, we are going to solve a problem from Codeforces. It is called Marbles, and it is an E problem from a Div.2 round. Monocarp is our main character here, and he has arranged n colored marbles in a row. His main goal is to rearrange these marbles in such a way that all marbles of the same color form a contiguous segment, and there is only one such segment for each color. And to achieve this, he can do the following operation any number of times. He can choose two neighboring marbles and swap them. We have to calculate the minimum number of operations Monocarp has to perform to rearrange the marbles. Note that the order of segments of marbles having equal color does not matter. It is only required that for every color, all the marbles of this color form exactly one continuous segment. We have these 7 marbles, which are 3, 4, 2, 3, 4, 2, and 2, and the answer is 3. And let's see why. On the first operation, I can just swap this marble of color 2 with its neighbor of color 3. For the second operation, I can just swap these 2 marbles, and the result is going to look like this. And of course, for the last operation, I will just swap these 2 marbles, and the result looks like this. And this is it. Now that we have understood this statement and the example, I highly suggest you to pause this video and think about the problem, because the solution is really nice. I surely enjoyed my time thinking about it. Let's count how many times each color appears among these n marbles. We are doing this because each possible solution is in fact a permutation of these colors. For example, this permutation corresponds to the following solution. We take the first color, which is 3, and we see that it appears 2 times. So we push color 3 2 times. We take a look at the next color, which is 4, and it appears for 2 times. So we will push 4 2 times into our solution. And the last color is 2, which appears 3 times. So 2, 2, and 2. If we choose, for example, this permutation, this corresponds to the following solution. So we need to find the permutation of this color, such as it takes as few operations as possible to transform the initial array of marbles into the corresponding one of that permutation. So we might start with a brute force approach, in which we try each possible permutation of these colors, compute the cost of transforming the initial array into the corresponding one, and take the minimum out of those. But the question is, how to actually compute the number of swaps needed in order to transform the initial array into the corresponding one. Let's say we chose the permutation 3, 4, 2. As you can see, I have to make sure that all the marbles of color 3 appear before all the marbles of color 4. All the marbles of color 3 appear before all the marbles of color 2, and all the marbles of color 4 appear before all the marbles of color 2. So, let's take the first pair, 3 and 4, and let's suppose I take a look at this array, but I ignore the marbles of other colors than 3 and 4. My array is going to look like this. So there is one operation that I need to perform in order for color 3 to be before color 4. Now let's consider the next pair, 3 and 2, and consider the initial array, but ignoring all the colors which are not 3 and 2. The array is going to look like this. I have to make sure that color 3 appears before color 2, so one swap is going to be needed here. And let's take the last pair, 4 and 2. I will also need one swap in order to make this right. I will swap the marble 2 with this marble 4. If we add this up together, we get to a total of 3 swaps, which is indeed the minimum number of swaps in order to transform this initial array into the desired one. So what we will need to do here is to compute the following 2-dimensional array, and let's call it min swaps, which is going to take 2 arguments, I and j. And its meaning is the following one. The minimum number of swaps needed to make sure that all the marbles of color I are going to appear before all the marbles of color j. This can be performed pretty easily using a technique such as 2 pointers, so it's going to be your homework. So let's say we have computed the min swaps 2-dimensional array. And here comes the fun part, guys, because we are going to solve this problem using subset dynamic programming. And we will build a 1-dimensional array, dp, where its meaning is dp of mask is the minimum number of swaps needed to correctly order all the marbles of the colors in the subset mask. Mask is going to be a natural number between 0 and 2 at power 20, And its binary form is going to represent our subset of colors. For example, if mask equals 20, here is how its binary form is going to look. We will have 20 bits, starting from the right to the left, indexing by 0, so 0, 1, 2, and so on. And here each bit represents one color, right? So if our colors are 1 indexed, let's say from 1 to 20, here let's suppose we will index our colors from 0 to 19. So we are going to take a look at what bits are set to 1, and here 4 is set to 1 and 2 is set to 1. So our subset is going to consist of colors 2 and 4. Now let's move on and find the recurrence relation for this DP. For each DP of a mask, we are going to see what are the bits set to 1 in that mask. So this is our subset of colors. When building this dynamic programming, we basically started from scratch, DP of 0, which means we don't have any color chosen. Then we are setting at each step some bit to 1. So we insert one color to this subset. Now, we don't know the order in which we have inserted this color, but that doesn't really matter. For some DP of mask, we will insert into this subset a color which is not inserted yet. And when doing this, we basically take the permutation of these k existing colors and pushing this new color into the permutation. Now remember from earlier that each possible solution to this problem is actually a permutation of these colors. And the cost of each permutation is the sum of the values in that min swaps array we have computed for each pair of colors I and j, where I appears before j in the permutation. The cost of the initial permutation was already computed in DP of mask, but we will have to add the cost given by each of these new k pairs. So we will start building the DP from DP of 0 equals 0, and for each DP of mask, we will try to insert each possible new color into the permutation. So we try each bit j, which is set to 0 in the mask. And for each of these j, we are going to update the DP value of the new mask with the new cost only if this new cost is better. And the value of the new cost is, first of all, DP of mask plus the sum of the costs given by the new pairs. And let's call it sum. So sum is equal to the sum of all the min swaps of I and j, where I is a bit set to 1 in the mask. So I is an already inserted color in the subset, and j is the new color we add. Of course, the final answer of the problem is going to be DP of 2 at power 20 minus 1. So basically the subset consisting of all the colors between 0 and 19. And don't worry if there is any color of this which doesn't appear in our array. The min swaps of that color and every other color are going to be 0. So they won't affect our DP. And the time complexity is 2 at power k crossed k squared, where k is the number of colors. For our problem, k is 20. But it can easily be converted into a better one, which is 2 at power k crossed k. And this is also going to be your homework, but one hint that I'm going to give you is to go to this sum, and instead of computing it in big O of k, because you basically try out each I, where I is a bit set to 1, try to compute this in constant time. Alright guys, this was the problem Marbles from Codeforces. I really enjoyed solving it. It is a super nice subset dynamic programming, and if you did too, don't forget to hit that like button, don't forget to subscribe and hit the notification bell button to be updated with my last videos, and share it among your friends. I'll see you on the next one. Andy out.